Good afternoon, and thank you all for joining us. This is the first webinar of the 2023 GLASE webinar series, and today's webinar is CEA and Combined Heat and Power, Perfect Together. My name is Haley Hawley. I'm the Extension Specialist with the Greenhouse Lighting and Systems Engineering Consortium, otherwise known as GLASE. And before we get started, I would like to thank our current GLASE industry and CEA members for their support. It's because of them that we can promote activities like these webinars and offer them to a wide range of audiences free of charge. I would also like to highlight one of GLASE's projects really quickly. This is free to all greenhouse growers in New York State who use New York State utilities and are a part of the electric system benefits charge. This project is called the Greenhouse Database and Benchmarking Tool, and it enables growers to receive a free energy audit and evaluation of their energy use. The results of this audit can then be benchmarked against other anonymous greenhouses, and you can compare how your energy systems are with commercially available equipment. So if you would like more information on that and to apply, go to glaze.org/benchmark or feel free to email me and learn more. So for our presentation today, remember that there is a Q&A box that you can find at the bottom of your Zoom screen. You can use that to ask questions about the presentation at any time, and we are going to save all of those questions for the end when we will do a live Q&A with the speakers. And today we are happy to have Thomas Bourgeois and Garode Foley from the U.S. Department of Energy's New York, New Jersey Combined Heat and Power Technical Assistance Partnership. They will be speaking about how combined heat and power can be integrated into CEA, as well as the project development process.
Okay. Time for me to share screen. I'm
Yes,
sorry here.
Go right ahead.
All right. So how are we doing? Can we see that?
Yep, looks good.
All right. Thank you very much. Thanks everyone for your participation here today. CEA and Combined Heat and Power, perfect together. This is a topic that we're really excited about. We thank you for taking your time. We're hoping to bring you both some passion and reason in today's webinar. Garode is here to ensure that reason prevails if passion starts to go off the rails. And our objective is to have today's session spark a dialogue with you all. I think we failed if you're not interested in connecting with us after today's webinar to explore some of the ideas and initiatives that we're talking about. And we hope that you will take advantage of some of the US DOE CHP TAP tools that we have to offer. So I'm going to, let's see, I am not, there we go. Briefly, we've gone through the introduction. We want to talk a little bit about unprecedented times ahead in energy markets. We want to speak to you a little bit about the benefits of CEA and CHP, including grid integration, value stacking, and energy cost savings. I'm going to turn it over about halfway to Garode, who will give you a much deeper dive into CHP implementation and funding. And then we're going to wrap up with next steps and hopefully how we can help with your projects. Quickly here, the US DOE has 10 CHP Technical Assistance Partnership or TAPs that cover all 50 states, 10 TAPs representing 8 institutions. I am in New York, running the New York, New Jersey at Pace University, working along with UMass Amherst. Garode services both our center as well as the Mid-Atlantic. The Mid-Atlantic is run out of Penn State University. So no matter what state you're in, what I'm saying here about the TAPs and what they offer would be relevant to you. Our DOE CHP TAPs have a variety of services. We get involved in end user engagement, end users being sites that utilize CHP or hope to or are interested in utilizing CHP. We provide fact-based and non-biased engineering support. We work in stakeholder processes, again, to try to reduce barriers to using CHP or to advance regional efficiency and energy independence, and to provide education to stakeholders, policymakers, and so on. One of the key activities that we undertake is technical services. We provide no cost, and by the way, all of these services are no cost. We provide no cost screening for CHP opportunities. If you have a site that might be interested, might be a candidate for CHP at a greenhouse or at any CEA location, we'd encourage you to please get in touch with us. We have several engineering staff members that will do a no-cost screening. Technical assistance, again, for end user sites. We have a national databases and information repositories to help support the market. And we're hoping today to try to identify some of our mutual interests and convene some follow-on activities here. Very briefly, I'm going to let Garode get into this in a lot more detail. I'm assuming that this audience probably has a pretty good idea of what CHP is, the concurrent production of electricity or mechanical power and useful thermal energy from a single source. CHP is distributed generation located at or near the point of consumption. In this case, we're talking about at, inside, or near the greenhouse or the CEA site. And CHP is a suite of technologies that can use a variety of fuels, including, and we want to stress this here today, because in New York State, Massachusetts, and elsewhere, we're on a path towards full decarbonization fairly quickly. CHP does utilize renewable resources, renewable natural gas, biomass sources, hydrogen, and we'll talk a little bit about the e-catalog. I'll leave that to Garode. The e-catalog is a DOE tool that identifies hundreds of different CHP packages and various prime movers and fuel sources. We now have half a dozen or more 100% hydrogen powered systems in the catalog. CHP is just the smartest way to use whatever fuel source it is that you're utilizing. If you have a CHP application, it makes a whole lot of sense. And we feel that the high-tech greenhouse is a particularly good application concurrent with CHP to utilize the otherwise wasted heat to provide efficiency, clean, reliable, resilient, and affordable energy at much higher efficiencies. And again, with the higher efficiency, lower emissions, lower greenhouse gas, lower CO2 emissions. And for many of you who may be already utilizing this, the greenhouse often operates by capturing CO2 from the exhaust gas and reutilizing the CO2 within the greenhouse, which is again another source of not only efficiency but also carbon CO2 reduction. A more efficient than separate generation, lower carbon and other pollutant emissions, lower operating costs. We want to stress this: working with any fuel, including carbon neutral fuels. And efficiency becomes much more important as fuels become scarce. We expect that with the movement away from natural gas in places like New York and New England and other places that are talking about a fairly rapid move towards decarbonization, these fuels, biomass, renewable natural gases, will be at a premium. Hydrogen, it just makes sense to utilize whatever fuel it is in a manner where the most energy will be recovered from the input fuel source. And again, I'm going to tee up a few slides a little later on from the New York ISO, which has been reminding us with their recent reports that we're facing unprecedented times here. Not facing, but we will see unprecedented changes in the grid, in the energy mix, which may have some implications for reliability and resiliency. We're not saying that for certain, but we do know that that there will be some challenges ahead. There may well be some challenges ahead. And on-site generation utilizing CHP does provide you with a greater degree of resiliency and reliability. And perhaps, we're going to speak a little bit to this, perhaps may provide a potential revenue stream with grid integration and with expected new grid markets, New York ISO and other New England ISO, perhaps PJM markets for grid integration. Finally, this does support intermittent renewable resources. We will need a lot of what the New York ISO is calling DEFRs, distributed and dispatchable emissions-free resources, DEFRS, in large measure as the grid decarbonizes. First, the grid becoming 70% renewable by 2030 and then 100% renewable by 2040. In order to make that renewable grid work, we're going to need a lot of dispatchable, distributed resources. And we're exploring the possibility, which we'd like to discuss at length with you folks, whether or not CEA might provide one of the solutions of a distributed, dispatchable, emissions-free resource. We do see unprecedented times ahead in Northeast energy markets, which we feel will create both some challenges and opportunities for CEA. Challenges because, as we see, perhaps increasing prices, changing out your supply, looking at new markets for supply, and also opportunities insofar as there may be new markets created. Not maybe, there will be. About this time last year, January 27th of 2022, we ran a webinar on CEA, and we had New York ISO Senior System Planner talking about, and I'm paraphrasing here, not an exact quote, but he said that the New York ISO markets are likely to change more in the next 3 to 5 years than they have in the last 10 to 15. And again, that may be of interest to CEA as to whether or not you can play in those markets. And if you have on-site distributed, dispatchable resources, if you can earn new revenues in those markets. So I want to let the New York ISO speak for itself. In a couple of new reports, the New York ISO published some very interesting work. If you haven't seen this, the 2021-2040 System and Resource Outlook, which they refer to as the Outlook, both the full report, the data sheet, and attached presentations is great reading. They highlight that roughly 7 years from now, an estimated 20 gigawatts of new generation, renewable generation will be required. And putting that into some perspective, 12.9 gigawatts of new generation have been developed in almost a 25-year time frame. And total installed capacity must triple 95 gigawatts to meet the 2040 goal. And again, with a little perspective, New York currently has 37 gigawatts of generating capacity. So we're running up from 37 gigawatts, what we have today, to a total installed capacity that is required to meet New York's innovative and path-breaking Climate Act by 2040. Extensive transmission investment is going to be required. And as stated, this is all extracted directly from the New York ISO's 2021-2040 Outlook. Unprecedented levels of transmission and generation investment will be necessary to achieve clean energy goals while continuing to meet grid needs. Not going to beat this too much to death, but shortly after they provided the 2021 to 2040 Outlook, they did a reliability needs assessment, the RNA. The New York ISO highlighted that short-term reliability margins are thinning through 2026. New York City in particular, the reliability margin narrows to as little as 50 megawatts in 2025. The CHPE is the Champlain Express. This is the new transmission pathway proposed to bring renewable generation down from downstate into the city, expecting an in-service date by 2026. However, as noted again by the New York ISO, there are reliability concerns that arise if there's any delay of that transmission of new renewable resources beyond 2026. And again, in red here, they've stated that even the slightest deviations from expected conditions, load forecasts, or project delays could trigger future reliability needs. And I am just appealing to what is said exactly by the, this is not with embellishment, this is strictly from what the ISO is telling us. So DFRS, I mentioned this, dispatchable emission free resources need to be developed and added at scale to reliably serve demand when intermittent generation is not available. Anywhere from 25 gigawatts to 42 gigawatts of DFRS will be required in the 2040 policy scenarios that the New York ISO has recently published. A lot of lead time will be necessary to meet that well in advance of 2040. They must be developed at scale well in advance of 2040 to be online and ensure that the flexibility of the energy supply and needs of the future energy system that New York is trying to build out. And this also goes, of course, for the same for Massachusetts, embracing much the same goals. So we have a little bit of a thesis here, and I said we're going to try to put passion and reason together, and hopefully reason prevails. We've thought a little bit about how CEA, CHP, conjoining food and energy can help develop more resilient communities, locally grown food, thermal storage, heat recovery in the greenhouse, carbon sequestration. We've done a little bit of publishing of this. We published some work last summer at the ACEE, American Council for Energy Efficient Economies, 2022 summer study on energy efficiency in buildings. We know that the Dutch have done some of this. This appeals a little bit to the Dutch model. Production of CHP at greenhouses in the Netherlands accounts for somewhere around 10 to 12% of total electricity sales in the Netherlands in 2021. So we know that the high-tech greenhouse is producing food at somewhere around this graph, by the way, which shows tomato production on 1 hectare open field versus the greenhouse with artificial lighting. This is from Dutch Greenhouse Delta 2021, 5 times productivity, 78% less water use. This too is from Dutch Greenhouse Delta 2021, looking at the first bar being the United States, the surface area in blue, second bar being the Netherlands, the surface area of land in agriculture being the very, very tiny blue, and then the Netherlands being the number 2 exporter of agricultural products by dollar value, second only to the United States on a much, much smaller land footprint than the United States. Again, I'm extracting from Dutch data. Natural gas-fired CHP in greenhouses in the Netherlands supplied 10.3 billion kilowatt hours, approximately 10 to 12% of total Dutch electricity consumption in that year. Also with measured estimated greenhouse gas reductions, which are pretty considerable. So this has been both an energy benefit, an efficiency benefit, and a carbon reduction benefit as well in the Netherlands. We asked the question, can the greenhouse here in the United States provide both power locally, power to the greenhouse, resiliency to the greenhouse, and resiliency and a dynamic asset to the grid? Does it support asset flexibility? This comes from the paper that I was referring that we had done at the ACEE meeting by our university and our center. Here we're looking at sites that have, we're looking at 2 variables here, going down the column, sites that have a high, low, medium, or high need for on-site power, and low, medium, or high flexibility. We find, for example, that hospitals sit in this box where they do have a high need for on-site power, but they don't have a lot of flexibility. The hospital does not want to shut down critical infrastructure, critical processes, to provide power to the grid. Whereas we feel, and again, untested hypothesis, that CEA might have that high degree of flexibility where it both needs power and may be able to allow for, turning down the lights, not utilizing the lights, turning down HVAC, whatever it may be, motors, drives, there may be some flexibility in the CEA process. And I'm quoting here to my right, a quote from the New York ISO. I mentioned that last year we raised this topic in a meeting with the New York ISO. They said that within the class of dispatchable resources, the most reliable resources are those that are already online. Let's say the greenhouse has already got CHP, it's online. And they also suggested that particular value will be paid for assets that are online, serving a load, and able to shed some of that load to inject that into the grid. That Swider is Robert Swider, who senior system planner, who spoke to us at one of our webinars last year. So again, motivation for this work, we're looking at the possible value stacking benefits of CEA with on-site power, providing both power and heat resiliency along with food resiliency, perhaps getting payments in new markets, although this will take us paying attention to the developments of those markets and making sure that CEA has a place at the table, talking about what they can contribute and identifying what they can contribute, enhancing economic viability without, we hope, sacrificing societal or business benefits. Allowing the greenhouses to provide power for greater penetration of renewables, meeting the 2030 and 2040 New York State goals, and addressing issues such as decarbonization, efficiency, equity, and resiliency. We're looking at future research, measuring carbon savings of CHP at greenhouses. I want to stress, and perhaps Garode will talk about this a little more because he straddles both the New York, New Jersey, US DOE CHP Center, and the Mid-Atlantic. The Mid-Atlantic is doing this more so in Pennsylvania, looking at high-tech greenhouses, replicable business models, talking to energy utilities in Pennsylvania. We feel that we do need to engage with the independent systems operators, the New York ISO, PJM, and others as they create these new markets to meet the dramatic changes driven by state carbon goals. And we would like to support CEA, GLASE, and others with the technical assistance, the education, and the outreach we can provide through our network of 10 DOE centers and the various tools that the DOE offers. So again, quick summary, CHP getting the most out of a fuel source, enabling high overall efficiencies, an increasing number of CHP systems that run on low carbon fuels, including RNG and hydrogen. CHP can be utilized in a variety of market sectors for different strategies, including resiliency. And most important to today's discussion, we'd like to continue this well beyond today to talk with your industry, with you, about how we might support particular projects, looking at particular sites, or working with you to provide unbiased technical assistance and provide resources from our national repositories, from site screenings through installation. With that, I want to stop sharing and turn you over to Garode Foley, who'll give you a deeper dive into CHP technical aspects. Garode?
Thank you, Tom. Let me just get my screen share set up here. And that one issue, Tom, you kind of raised there just at the end. I think we can kind of get back to that, but certainly some interesting kind of thoughts in the Mid-Atlantic region and it was really about trying to integrate with local municipal utilities, who we believe are much easier to sell at a proper retail value, any excess energy that might be available. So that kind of would solve one of the economic issues we have with CHP in the United States. Holland being a great model, they're very well compensated for any excess electricity that's pushed into the system because the system recognizes the benefits that are available. So what I want to really do here is to talk through the project development process. I'm going to touch very briefly on costing and funding opportunities, but it's really an attempt to kind of demystify CHP project development. It's quite complex. It's certainly a lot of equipment and a lot of engineering, not exactly native to the agricultural industry. You guys deal with a lot of technical stuff regarding lighting, etc. So this is on the power production side. So I want to kind of walk through this. I'll walk through it pretty quickly. What we're looking at here, just project costs and funding. I'm going to do a little bit on that, and then I'll get into just some of the sort of meat and potatoes of actually developing a CHP project. So from a cost perspective, capital costs, of course, owner development costs, as we go through this, you kind of get a little bit of a sense of some of the permitting stuff, some of the legal stuff that's necessary. So, that is a cost bucket. Engineering, procurement, construction, EPC, or your standard, ingredients into any project. And then I'm going to touch shortly on grants, loans, and tax credits, which have become extremely attractive with the introduction of the Inflation Reduction Act and some financing options. First of all, and this is a table, the citation is at the bottom of this, and I'm assuming this slide deck will be available, or certainly anybody that wants it can reach out, and we'll be happy to make this data available. Here, we're really looking at just the total install cost. This is a national figure, representative, and to some degree depends on technology, and to a larger degree perhaps depends on scale. Bigger always being better and cheaper and easier to implement on a per kilowatt basis. But your total install costs, really for the type of what we would envision here is a couple of 2 megawatt engines, reciprocating engines with all the accessories required. Really rule of thumb numbers in the 250 to or 2,500 to $3,000 per kilowatt, just to kind of put a flag in the ground on cost. So about 2.5 million to 3 million per megawatt is your typical capital investment for these type of projects. From the funding perspective, there's quite a number of opportunities out there to source funding. So, we understand there's significant capital cost with this. Of course, self-financing doesn't require a lot of conversation. Traditional financing is certainly available to these kind of projects, with leases, potentially being provided from banks or third parties, but often commonly from vendors, so that a significant portion of the cost could actually be funded through an equipment lease, for example. That might be 50% of the cost of the entire project. In terms of loans, it's not just obviously commercial loans, of course, but also below market loans. So the Green Bank, as an example of a facility that will provide below market loans and do incorporate currently CHP in their portfolio. And then more on the specialized financing, some utilities offer financing through just on-bill billing, which really is helpful in kind of generating positive cash flow despite the large investment, but having the ability to generate positive cash flow from the beginning. PACE, the property assessed clean energy style funding is certainly very attractive for these projects, and again, is used to fund these projects. That's where the capital cost effectively is like an added assessment to the project, and it keeps the assessment and the obligation with the project. So it has some flexibility in terms of ownership here, which can be quite useful to CEA developers. And then under the energy services banner, we have a variety of options, generally from third parties who will come in and develop the combined heat and power supply portion of your project and supply you energy at, one would assume, less than market rates to the facility on an as-needed basis. You don't make the investment, the third party does, but you are obligated, obviously, to repay that third party, and in some cases to assume an obligation to offtake a certain portion of the output over a period. Typically, a lot of these funding type schemes would be in the order of 12 to 15 years. In longer is easier on you, but generally you need investors to kind of support that, so their return requirements might dictate more in the 12 to 15 year type time frame. The IRA certainly is a game changer as far as we're concerned in the combined heat and power business. And again, you can have access to these slides, so I'm not going to read through everything, but the essential statement here is that there is a 30% investment tax credit available to investors or to owners for implementing combined heat and power. That's 30% of the entire project cost. There is a requirement that you do meet prevailing wage and apprenticeship requirements. That effectively, the easiest way to do that is to use union labor, and then you kind of comply with both typically. There are options if anybody is from a nonprofit or government type agency that traditionally doesn't pay taxes and therefore can't really use a tax credit. And you're sort of forced to go through a third party that has its own issues and costs. With the IRA, it has developed a scheme where you can actually, as a nonprofit entity, can get to the same or a similar value and actually can get a production credit for the output. And it's sort of done through the IRS. It's essentially a production tax credit, a PTC. But it's very useful if you're a non-tax paying entity, if you're a governmental or a community entity that doesn't pay taxes, that is tax exempt. Projects under 1 megawatt, probably not very relevant. Maybe some smaller vertical farms, but not generally very relevant. But the 1 megawatt is exempt from the prevailing wage and apprenticeship requirements. I'll move on here. You can also get an added 10%. So you can move the 30% tax credit to 40%. For two general reasons here. So the energy community bonus is really for brownfield sites, as listed here. It's generally sort of focused around communities that had relied on coal power. That was kind of a concession in the development of the legislation. So in those communities where there's unemployment related to the kind of moving away from coal power, locating in those communities will allow you to actually get an added 10% to that tax credit. And then a much more accessible one is the second one here. You can also get a 10% bonus for domestic content. You see the basic outline here. It does specifically, you can see here in the highlights, it must use 100% domestic iron and steel. And then, percentages, and you can see how that percentage increases over time, but beginning in 2023 at 40% of the remainder of the project or remainder of the equipment to be US provision. And that's very attainable on both counts. So lots of opportunities here to actually get a 40% tax credit for these projects. There is a couple of things to note here. You need to break ground before January 1, 2025. So we've got 2 years between now and then to essentially develop, plan, and start the project, not complete the project. You just have to break ground within 2 years. After that time, it changes to a tech neutral credit, and it's really driven by fuel input. So at that point, you would have to be using a carbon neutral or non-carbon fuel to drive whatever technology you're using. And in that case, you would continue to be eligible for tax credits. But the current plan is that, you know, up through the end of 2024, you can pretty easily avail of a very significant tax credit. That's potentially 40% of the system costs as a tax credit. And that also can be combined with any other credits that are available in the community, whether it's local, regional, utility, state, can be additive to the tax credit from the IRS. So project implementation, that's kind of what I want to get into, and I'm going to kind of read through it here a little bit, just to give everybody a flavor of it. As Tom said, you know, this is our job and our mandate is to be here and available to anybody that's interested to further these discussions on any particular topic. So please reach out. But, you know, as I mentioned at the outset, certainly development of combined heat and power is multifaceted. You've got thermal, you've got electric, you've got permitting on various fronts, and they're the things I'm going to take us through kind of quickly. And, you know, the theme here is if you plan well, there's the 7 Ps. I won't quote them because it involves a couple of words, but it's essentially saying that, you know, poor planning has poor outcomes, and that's certainly very true. The more complex the project is, the more truer that becomes. So, you know, we would encourage anybody considering CHP to, you know, the planning stage is the all-important stage. And when we're getting into project development, you know, at this point, we sort of understand our funding, we have a direction from a financial perspective. And in some cases, you know, the financing may in fact dictate some of the design parameters. So, you know, we're considering we're past that. We understand the obligations on the financing side. And so let's get into kind of project implementation. So again, we've done our screening. This is, you know, as Tom said at the outset, we're available to assist with that. You've gone through your in-depth financial analysis. You've kind of put together a concept and you're really ready to put it to the test, put it on hard paper, on hard copy, and start getting it financed. So now you're moving into the area of getting environmental and site permits. Yes, you know, you're not going to commit to financing until you're kind of through a couple of these stage gates, but you have it set up, you understand what it is. Biggest task here is really the EPC, contracting with the engineering, construction, equipment supply firms, general project management, and then commissioning. And commissioning is a significant issue on a combined heat and power project, just again because of the technical nature. Just a sort of a couple of pictures here and highlighting some of the aspects of what we're dealing with combined heat and power. Top left, you know, that big large tank is a hot water storage tank. It's an important component to successful combined heat and power specific to CEA. It really plays a very vital role, and yes, it is very large. On the top right-hand corner, you know, air intakes and exhaust. So it's not just the obvious air permits, but actually just running air through significant volumes of air for combustion as well as cooling. When you're dealing with reciprocating engines, if you think and calculate the amount of air that you require to make combustion happen, multiply that by a factor of 10, and that's the total combined air you need for combustion and cooling. So the cooling air, when you have housed systems, is very, very significant. You also see the oil coolers, dump radiators. So again, we have, you know, a lot of thermal stuff going on here. The objective, as I say in these projects, always I never want to see one of those radiators fans spin, because that means you're using the heat for useful purposes, but they are a necessary protection for the engine. Bottom left, and this is kind of really particular to CEA, and one of the really interesting synergies that we have here is, of course, you can recover CO2 from the exhaust, and there are, you know, that is a commonly done for these, and I think anybody in CEA world understands the value of CO2 all of a sudden has become something of a consideration. So here you can kind of generate on-site liquefy store so that you have plentiful supply to keep you going even when the engine's not running. And then on the bottom right-hand corner is kind of one of the essential components of heat utilization. So lots of heat exchangers and pumps to kind of harvest the heat from the engine and push it through the greenhouse. When it comes to selecting vendors, and we're not trying to make your mind up or tell you anything that you kind of don't probably know already, but when you're self-developing, particularly when it's you can push a lot of this stuff off to a third party, but I think a lot of you guys are hands-on, so if you're moving forward, what we're looking for in terms of vendors are people that have certainly CHP projects experience. But to me, more important is having experience with a similar industrial application, we call it here. I really want somebody that's sensitive to CEA world, that understands the proclivities of the industry, the operating schemes, etc. So I would sort of, in my scoring, I typically give that a higher score than actual CHP experience. Successful project track record. I can't emphasize enough to please check. Just because somebody says they have 10 successful projects, I would like to, check a couple of them and make sure that they are successful from the owner's perspective, not just the vendors. And I like to see in-house resource engineering in particular. I want to have engineers on hand. I don't want my contractor, being completely subservient to the vendor when it comes to answering technical questions. And we always use an RFP process, almost no matter how simple or complex, just to level set and make sure that I'm getting the best value for money. I think, if you're going to buy a clothes dryer, you're not going to buy the first one you see. You're going to probably check around a little bit. So in the RFP process, there's a list of things here that we want to suggest you should ask for. Description of the project, give them information, make sure you understand the scope of service and make sure they understand the scope of services. That's where there's a lot of disjoint. Ask them for references, detail on their previous history. A lot of this is kind of template stuff they have. It's available. Just ask them for it. Don't be afraid to ask for it. Let them describe the technologies. Let them describe how they're going to satisfy your need. Don't assume that they know. Financing, if they have financing available, let them put it in there. Offer a schedule. And an operation and maintenance plan for combined heat and power. O&M is a very significant consideration. It's pretty regular. It's significant. It's a cost item. We carry it in every pro forma. So let's see that in the RFP, even though the vendor that I'm talking to may not be the one that's going to provide it, let him give us his impression of how that fits in, and I certainly need that in my pro forma. And so, this just typical documentation that we've provided in RFPs. I mean, we will put out 70-page technical documents to combine with the 30, 70-page legal documents in an RFP. You need to be specific on your requirements, both the performance, schedule, equipment, etc. And provide them all the information they need. So we have gone ahead and we have provided a significant amount of information, such as doing special geotechs in the area we anticipate that this will be located on. So I don't have change orders coming back at me saying, well, we didn't realize the pad had to be 12 inches. We thought a 3-inch pad would be sufficient, but your soil doesn't have the bearing capacity, so we need more steel, we need more money. Fight that up front, it's a lot cheaper. Zoning and planning, for sure, this is a significant issue. Your locations typically are not in the middle of urban areas, and if we're dealing with urban vertical farming, typically the equipment is probably inside anyway, but be aware that there are multiple jurisdictions here. And so you have county and city planning bureaus that do govern land use and zoning issues. So you have to make sure that you're zoned for this. And they could require that an environmental impact assessment is carried out. And so, be aware that these are here. You get to these up front and early, they really are not a problem. They're a huge problem if you're unaware of them or ignore them. So talk to these people. Don't be afraid of them. Talk to them. Go out and ask them. And state and local building is almost, the whole separate tranche of sort of planning and permitting that's required, including fire officials, safety officials, etc. Again, it's all pro forma stuff. They do typically carry fees, but the technical, what you'll end up finding, of course, is that more about the technology than they do. They're just looking for a level of comfort that something stupid isn't being implemented here. And I think that's kind of the extent of a lot of the reviews. And again, hit these early, understand what they are, and they will not be problems. Pictures on the bottom, just give you an example of what we do. The left-hand picture is the existing picture. The right hand is just a rendering of what it would look like after the additions were made. In this case, we're putting CHP inside that building and removing a window and changing a few things and pretty simple stuff. Again, as long as you're ahead of it, it really doesn't become an issue. Do recognize noise and setbacks, and in particular noise, particularly for at the neighbor property line is usually where it's measured. Again, is something that has to be incorporated. The earlier you do it, the better. You can pretty much get to any noise level that you require, through various treatments to the equipment housing and the exhaust system. Again, just be aware of it up front. It's not a problem. If you have to retrofit something, then you got a problem. Again, lots of codes and standards, mainly around fire safety, electrical, structural installation. It's generally about life safety. So, they're not in the weeds wanting to know what color the controller is. They really just want to make sure you're not going to electrocute anybody. And of course, air emissions. The electric grid as well, you are most likely going to tie into the electric grid. Currently, that's to sort of be able to support the greenhouse when you choose not to operate combined heat and power, or when it's taken down for service. Hopefully in the future, that would be to transact energy back to the grid when it's of high value, in which case you have a tremendous asset on your hands that can really generate some revenue, positive revenue. So there is some engineering work required here. So you are starting to dip your toe in the water. You are starting to spend some money, but it's light engineering. I'll suggest that the forms that need to be filled out and sent in and signed by an engineer is probably a $10,000 or less obligation, and something that should be started early in the process. Air emissions, I don't have to tell anybody about air emissions. It's a good thing that we are conscious of air emissions, and this is outside of decarbonization, just sort of straight air emissions. So we are cognizant that we are required to meet certain performance criteria. The pollutants they're concerned with traditionally are NOx, CO, and sulfur dioxide is really not. It's on their list, not an issue if you're doing a natural gas, typically fired reciprocating engine, particulates likewise. If you're doing biofuels, that would be a different story. If you're doing wood, there's quite a bit of sulfur in wood. So, it may be a concern depending on your fuel type. Generally for natural gas, I'm really concerned with NOx primarily. And it depends on your region's environmental status or its compliance status with federal air regulations, whether it's in compliance or non-compliance, as to how much treatment you need to add to your box. And again, this is something you want to understand early. This should really be understood in your screening area. And it's all pro forma stuff. Talk to we can help you understand the options. I'm not going to be understanding necessarily the local airshed region. You can talk to them, but we can certainly help you prepare for that conversation. And then do acknowledge, of course, that once this is built, you will be subject to air testing to prove that you are actually meeting the requirements. And, this is an example, and this is a project we did. It's an inner city environment, in which case we were actually required to do some dispersion modeling to prove that formaldehyde was not going to be an issue. We do produce anything that combusts natural gas is going to produce a certain level of formaldehyde. It used to be de minimis. Today, those thresholds have sort of come down, again, depending on your local jurisdiction. And while this is a daunting task and kind of scared the hell out of us when we were told this in the middle of our project due to an EPA rule or DEP rule change, it turned out to be, it's a $7,000 study that was required. And yes, it's more money, and yes, it's more work. But again, getting these things to these things early and kind of grasping them with both hands generally eliminates them as a concern. Again, it's a little bit of a repeat. We said planning, zoning, utility interconnection, environmental compliance, and construction permits are all essential steps for sure. And I think the point here is, I want to be sure, I want to understand this very well. I need to know what's ahead of me before I finalize the design, particularly when it comes to noise or emissions. If there's a requirement there that forces me to change the size of ductwork, for example. So noise, the real noise issue is around that cooling area. So, massive, we're talking 60,000, 100,000 CFM for, you're talking about a 2, 3, 4 megawatt system. That's the kind of air movement you're talking about. The bigger the ducts, the less the noise. It's very simple. So, does the noise criteria force me to do bigger duct? Does that force me to do some other accommodations to the design? You'd like to know that up front, and sometimes it will influence your design. And again, be aware that the full process, not, you need to understand early what the requirements are and what you're designing towards. The full process between application, review, and approval can be 3 to 6 months. So this is something that we would suggest start early. And again, call the local agencies. Don't be afraid to talk to them, reach out. And so that's kind of just a very quick drag through the development process and some of the highlights there. I think that this is, one little segment here on package systems. This was actually really developed under the inspiration of NYSERDA, who started what they called a kind of a CHP catalog that was picked up by the Department of Energy, who have really advanced the packaging of these systems. And whether it's a single fully packaged or it's a modular multiple component bolted together at site approach, generally, I'll suggest the reason I'm bringing it up here is I think this is very compatible with what a lot of you are trying to do in the CEA world, and this really meets the needs. It does certainly reduce costs, and it also is, creates a much more predictable cost basis moving forward. So that's essential in my world. It's not so much about the ultimate cost that I get approved from some CFO. It's much more, my concern is always about, how accurate I am, the predictability of that. You never want to go back to the CEO telling them that you're 10% short. So modular systems help you with that. Have resulted in cost reductions. It's easier for the manufacturer to repeat the same thing in his shop and send it to your site than to sort of try and make it happen out at site. There's efficiencies of multiple kinds there that help to reduce cost per kilowatt, and it also reduces time to market.
Road?
Yes.
Could we wrap this up in the next minute or so? We do have a couple of questions.
We certainly can. So I've
Great,
gone through
thanks.
the benefits and again, I kind of talked to this cost reductions, 20% or so, significant cost reductions potentially, and time reductions. This is just a reference. You'll see this. We would encourage you to check this. Lots of really great technical information. The e-catalog, if you just Google DOE e-catalog, you'll get this great resource. Tom mentioned it earlier on. A listing of resources here available. And I'll stop there. And Tom, if you want to jump in here.
Just to say, please ask us questions. And also please talk to us afterwards. I know we've only got about 5 minutes left, but we love any questions. And we have a lot of services. We have a lot of support nationally, including data repositories, tools, catalogs. And we would like to come to your site or provide end users background information. And with that, Haley, let's take some questions if we can in the next couple minutes. Thank you.
Great, thanks so much. And I can also put your emails when I send out the recording so that everyone who sees that email can contact you directly. So our first question is, can you talk a bit more about what the state of the market is for carbon capture technology for the less than 1 milliwatt projects? It's appearing that on that scale, the economics don't quite shake out for capturing that CO2 for greenhouse use, but we would love to know if anyone has been able to make that work.
Tom, maybe
if you want to look over the question, it's in the Q&A box that you can look at too.
No, the question's understood, and we do have examples. It's relatively new. So carbon capture is a sort of an old and fairly dumb technology, and it can be scaled down. That's not really the issue. What's changed is the value of CO2 to enable people to justify carbon capture economically rather than importing carbon. So it is a short answer, Haley, is that it is scalable, and yes, it does work down to a half a megawatt without much problem. We can provide some citation, not a lot, because it's the value of CO2 that now drives it, but technically not an issue for sub 1 megawatt.
Okay.
I don't have anything to add except we can provide some examples. There are sub megawatt examples, and we can provide them.
Great. Similar question, can CHP in general be implemented in small scale family operations?
Giro, do you want to take that one? I mean,
yeah, I mean, again, the simple answer is yes, but with the caveat that costs do scale with size.
Yeah.
So there are a number of vendors out there with 50 kilowatt, 25, 50, 100, multiple choices out there in the 100, 150, 200, even more in the 500. So I would suggest that I hate to prejudice people, but I'll suggest that if you're sub 100 kilowatts, it's very difficult economically. Technically, again, feasible, but economically, it's the same cost to do the permit, same interconnection, not exactly the same engineering, but not much different. So it gets really expensive, and between 1 to 0.5 megawatt is in the expensive, but and above 0.5 megawatt, certainly above 1 megawatt, is very economically justifiable.
yeah. Yeah.
Anything else to add?
No, no.
Okay.
As Giro well stated, the smaller systems are going to just be a lot less cost effective. They may be right for a resiliency play. They're just not going to be that cost effective. And but as you get up into the higher size ranges, 0.5 megawatt, 1 megawatt, above 1 megawatt, and particularly if we see markets where where CEA might get paid, becomes ever more attractive. And I can think that's what we're focusing on: the larger size, and also focusing on the fact that we may see market opportunities, secondary revenue streams that might make this all the more worthwhile.
Great, thank you. Let's do one more question before we close out here. So what is I guess how many commercial greenhouses are implementing this right now in the US? Is this completely new? Do some greenhouses have it already implemented?
Not completely new. We know a couple in New York, and I get calls more and more so recently. I've had 4 or 5 calls in the last just 2 months about sites interested in CHP at greenhouses. So we have working examples, and B, there's obviously a lot more people looking at this, at least based on the volume of calls I'm getting. Garrod could probably put even more on that, because I think in Pennsylvania, you're probably seeing more activity than we're seeing in New York.
Yeah, I mean, but Tom is right. There are plenty of examples in the US. We really are at the beginning, I think, of the growth of CEA, and we are certainly seeing the influence from many of our Dutch friends who are an integral part of that movement. And they kind of come with an attitude that, you can't build CEA without CHP. So yes, we're seeing a spike in interest, which is really, I think, reflecting a spike in development potential for CEA and driven by people that have really more involvement in the technology, the people coming over from Holland and other areas. I don't want to make it exclusively Dutch, but their experience suggests you wouldn't build this without CHP. So we don't have hundreds of examples in the US because we really are at the beginning of the CEA development scale here, I think.
And by the way, if anybody on the line has a quote showcase exemplary project, I think we have 1 or 2. One of the things DOE does is we highlight exemplary projects that are, available in a national repository that you can pull out by fuel source, by size, by state, and also by sector. I think we have 1 or 2 greenhouses. There's a couple of greenhouses. There's one out in California that I believe we have a project on. Anybody on the line has a project they want us to highlight, let us know. We'll get more CHP at greenhouses in the national repository. That would only be beneficial. And again, based on the calls I'm getting, I'm seeing more and more people interested in this, in greenhouses in New York, New Jersey, New England, and the Mid-Atlantic.
Great. Thank you so much. That's a lot of really great information, and I will send the recording to this out with your emails. And if you mentioned you wanted to send the slides out, so we can do that as well. And I encourage all of you watching to contact them if you have any questions or interested in doing this in your own greenhouse.
Thank you so much.
Thank you, Hallie.
Thank you.
Thank you, Haley.
Yep.
Have a good day, everyone.
Okay.
Bye.
Bye.